So we can create these conversion factors from chemical formulas of the moles. And here we're just using, what would it be? It's like an ethane, but it's got 4 chlorine groups and it's got 2 fluoro groups. So we got 4 chlorines and 2 fluorines. And so we can derive these mole conversion factors or mole ratios from just the formula, because right, how many carbons are there in this molecule? There's 2. So if I have 1 mole of the whole molecule, then if I could take out just all of the carbons, I'd have 2 moles of the carbons. And same kind of idea for the chlorine, because there's 4 chlorine atoms in here. In 1 mole of that molecule, I can pull out 4 chlorine, or 4 moles of chlorine atoms. And these are all just in, again, moles, in moles, not masses in grams. And this is super useful a lot of the times when you're doing the kind of stuff we are. And so we can use it to figure out like the mass of oxygen in a 7.2 gram sample of aluminum sulfate. And there's actually 2 ways now that we could do this. Right? We could come up with a mass percent of oxygen, and we can come up with the mole ratio. We'll do the mole ratio. All right, so the mass of oxygen in a 7.2 gram sample, 7.2 grams. Al2, SO4, 3. I can start doing this. So if I'm going to use the mole ratio, what's the mole ratio? How many moles of oxygen are there for every 1 mole of aluminum sulfate? Say 2 oxygens? 12. Oh, okay. 12. Yeah, so I got 12 moles of oxygen for every 1 mole of Al2. And it's supposed to be an L. SO4 3. So what do I need to convert aluminum sulfate into before I can use that ratio? Moles. So I need a periodic table. I can print periodic tables. Let's see, this is aluminum. (26.982, 32.06, 15.9). Calculators in scientific mode. Okay, 342.132 grams. And that is the mass of 1 mole. Cool, and then our mole ratio is 12 moles oxygen for every 1 mole Al2, SO4, 3. That seems like a lot, and it seems redundant to maybe write this out over and over again. The Al2, SO4 is 3, the aluminum sulfate. But it will save you a lot of mistakes in the long run. Just keeping those units straight. And I did something wrong. What did I do? Oh, mass of oxygen. So what was I missing? Conversion to mass. And here we want to make sure we use, because we said moles of oxygen, just a single oxygen, Oxygen's one of those diatomic elements, but here we're using the single monoatomic. So 15.999. All right, I got 3. I multiplied by 12 instead of 15.999. That'll do it. Yep, 2 sig figs, 4 grams of oxygen. Cool. Any questions? Okay. Determining an experimental formula from empirical data. Oh, I can't remember. Did this class, do we get to do this? Maybe. You determine the empirical formula, and then I think the way that you get the molecular formula is cool. So empirical formula can be determined from elemental analysis. We saw that earlier, right? We just said Lavoisier took these, I think it was Lavoisier, took these things and breaks them down, and then he counts or measures how much mass of each thing, and that's came up with the law of definite proportions. When you do this kind of analysis, you can also determine the empirical formula of any compound that you do the analysis on, as long as you can account for all of the elements. So an empirical formula represents a ratio of atoms, or a ratio of moles of atoms, but not masses. And more specifically, the empirical formula is always the simplest ratio. So it's not going to give us the molecular formula necessarily. Sometimes it will, sometimes it won't. All right, so this is a long procedure. Depending on what you're given, you're either going to be given the mass of each element present, or you'll be given the mass percent of each element present. If you're given percentages, then you just convert percentages to grams, and assuming you start with 100 grams of the compound. Why do you assume 100 grams? Because it's percent. It's the easiest thing to calculate. You could pick literally any number of grams. 100 is the easiest, right? If I have, I think it was like 69.94%, I think it was iron by mass, right? If I had 100 grams of whatever that compound is, how much iron would I have? 69.94 grams, right? So it just takes the percents and converts them straight into grams. You don't need to do much other than that. And then you convert each of the masses to moles. And this is key because, like I said up here, it's the ratio of atoms or ratio of moles of atoms, not the ratio of masses. So we can't use masses because atoms weigh different things. So we have to convert them into moles. And then we divide the moles of each element by the smallest number of moles. And that'll give us formula subscripts for each element. So sometimes you'll get fractions. Within this class at least, if you're within 0.2 of a whole number, then you can round it to the whole number. If it's anything farther away than that, you're going to have to work out some fractions. But I'm sure we'll have an example of that. So for example, these are the fractional subscripts. For me, it always helps to remember these as 1 divided by whatever you would need to multiply it by, because 1 divided by, sorry, not 2, 5 equals 0.2. 1 divided by 4 equals 0.25. 1 divided by 3 equals 0.33, repeating. And then this would be 2 divided by 5. You see that 0.2 to 0.4, that's a whole multiple. Right? So these fractions are all related. And then this one's 2/3, this one's 3/4, this one's 4/5. Right, so that's why you multiply by each of these numbers, because if I take 4/5 and I multiply by 5, it gives me 4. Right, so it converts it to a whole number. You don't just do that for one subscript, but you do it for all the subscripts. All right, we're going to try and do these sort of as quickly as possible because there's just a lot of steps. All right, so a sample of compound is decomposed in a laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, 220 grams of oxygen. Calculate the empirical formula of the compound. Okay. So we were given grams, meaning we don't need to do the thing where we multiply by 100s. That's only if you're given percents. We've already got it in grams. I like to set these all up at the same time. So if we got 65 grams of carbon, or 165, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Let's do it this way. All right, so we need to get each of these into moles. So divide by 12.01. Whoops. Because 1 mole is 12 grams, 1.01 grams. Okay, so 165. You don't need to keep every single one of the decimals here, just like 5 decimal places. It's usually pretty good. Don't worry too much about rounding. Okay. Hope everybody's good. All right, converting grams to moles. Just in case you didn't know where I got those numbers from the periodic table, 12.01, 1.01, and 16. So what do we do next? Divide by the lowest amount. Which one's my lowest amount? Carbon? Yeah. Let me ask you this. Could I also divide by oxygen for this one? Pretty close. So that'll tell us, actually, what does that tell us about oxygen, the amounts of oxygen and carbon in this molecule? About the same, about 1 to 1. Anyways, so just divide by the lowest though. So we're going to divide by 13.73855. So this will be 1 carbon. So we need to do C. And then 27, 5. I'm just going to put a ditto there. Same thing. That's 2.00346. I mean, I guess I should just... That's 1.00174 oxygen. All right, I don't expect you every time to write out all of those decimals. Just doing it here to illustrate the fact that, is that closer than 0.2 to a whole number? Yeah, that's basically exactly 2, right? And same with the 1 here. So you might even notice before dividing on a problem like this that 27.5 looks like it's about twice as much as 13.73855. So you just write 2. So we can drop all of those, we can drop all of these. So that means that we have 1 carbon, 2 hydrogens, and 1 oxygen. So that's the empirical formula. Also, I am planning on getting to uploading videos this week. Had to do my self-evaluation for the last few weeks, so that's been eating a lot of time. But that's done. So, any questions about that one? We see another one. I think the next one should have a. Sorry, make sure there weren't any questions. Oh. All right, so ibuprofen has the following mass percent composition. We want to find the empirical formula, so what do we have to do first? Convert them from percentages into grams. And what do we multiply by? 100, because it's the easiest. So I'm going to take all of these and multiply by 100, because that'll convert them into grams. So this is going to be 75.69 grams of carbon, 0.80 grams of hydrogen, and 15.51 grams of oxygen. Okay, actually, what I'm going to do, let's see, let's do 3 minutes. I think if I do this, okay. So go ahead and work on it. And if you beat me to it, feel free to compare to somebody next to you. Frantic scribbling. Okay. Magic. So what do we have to do with this one? Right? Problem is that we have this. So what this is saying right now is that I need 6.5 carbons. Can't have half a carbon would be beryllium, lithium. 3 protons? Can't do that. It'd be a different element. So instead of that, we see 6.5. 0.5 is a half. So if I multiply by 2, that'll make all of these a whole number. It'll make the 6.5 a whole number, and we just multiply all of them by 2. So this will be 13, 18, and 2. So this will be C13, H18, O2. Cool. So that's for the empirical formula. How do we find the molecular formula? Experimentally, you look at freezing point depression or boiling point elevation. But we'll cover those later. For now, to find the molecular formula, you have to have the empirical formula given. So somebody has to say, this is the molecular formula, or the molar mass, I should say, of the molecular formula. And you divide the molar mass of the molecular formula by the molar mass of the empirical formula, because the molar mass, or so the molecular formula will always be some whole number integer, which I guess is a little bit redundant. It'll be like 2 times, 3 times, 4 times, however many times more of every atom in the molecule. So molar mass divided by molar mass of, I should write this in here, of molar mass of the molecular formula divided by the empirical formula molar mass will tell you what you need to multiply your empirical formula numbers by to get the molecular formula. All right, so we've got a compound. We'll say we did all the work. We found the empirical formula is CH, and it has a molar mass of 78.11 grams per mole. Now this is the molar mass of the molecular formula. It's not telling you that CH has a molar mass of 78.11. So what we'll need to do first is say we've got carbon and hydrogen. There's one of each, so times 12.01 times 1.01, because this will give us the empirical formula. So it's 13.02. So that's grams per mole. So that's the molar mass of the empirical formula. And so yeah, the 78 larger than 13, right? We're always going to end up with some whole number here. So if you divide it and you get a number that's smaller than 1, then you've done it backwards. So if I take 78.11 and I divide it by 13.02, that equals 5.999231951. Right. And there's always going to be a little bit of this nonsense over here because there's always a little bit of experimental error. And there's also, right, error in, this is 78.11. I also only use 2 decimal places over there. So if we think about this, how many decimal, or how much precision do I have on this? It's the smallest number of significant figures that I used. 3, right? Hydrogen is 1.01. Whoops. So that would be 1, 2, 3. So that should round up to 6. Now, in this case, just knowing what we're trying to do, that we're calculating this factor that we need to multiply, really it's carbon, which is 1, and then we'll multiply it by n, and then hydrogen, which right now is 1, and we'll multiply that by n. We're trying to figure out what N is, because we can't have partial atoms. So I made that kind of small. So if I take carbon, which I have one of them multiplied by 6, this should be C6. And then the number of hydrogens multiplied by 6, H6. That's the molecular formula. Okay. Go a little bit slow. So one way that you can do this elemental analysis for specifically compounds that have carbon, hydrogen, and oxygen is combustion analysis. Because if you burn that compound, and you burn it completely, you're always going to end up with carbon, hydrogen, sorry, the carbon as CO2 and the hydrogen as water. And then the original mass of oxygen, if there was any, will be the extra that's left over. So if you know the amount of CO2, the mass of CO2 that's produced, and the mass of hydrogen that's produced, you can work backwards to figure out the mass that came from, the mass of carbon that came from the compound that you burned. So it looks something like this. So you'd have some H2O absorber, so this will hold on to all of the water that comes out of your reaction, a CO2 absorber that holds on to all the CO2. And of course, you know the mass of all the stuff that's in here before you do the experiment, the mass of everything in here that's before the experiment. So you burn your sample using oxygen, it burns completely. Since the water and the CO2 both get trapped, then I can take those afterwards and reweigh them. And since it's trapped in a solid form, right, we can get the mass and then figure out what the empirical formula is. So upon combustion, compound containing only carbon and hydrogen produce 1.6 grams of CO2 and 0.819 grams of water. Find the empirical formula of the compound. So there's kind of two ways that we can do this. What are the two ways that we can figure out the mass of, or what's one way we can figure out the mass of carbon in this 1.6 grams of CO2? Huh? Yeah, percent mass composition. We could also do it by moles. The moles might actually be more efficient. Because if we start with the moles, or we start with the mass of CO2, right? Eventually, for our empirical formula, we need to know how many moles of carbon there are in this anyway. And just by looking at the molecular formula, right, what would the ratio of moles of carbon to moles of CO2 be? 1 to 1 for carbon, right? We're not concerned about the oxygen here. Any of this oxygen, because we're also told that the carbon and the hydrogen, that carbon and hydrogen are the only elements in the compound, so we're not concerned about the oxygen. I can do this and then just use the molar mass of CO2. Just 44. Because that'll give me the moles of CO2, and then like I said, like we just said, 1 mole of CO2 has 1 mole of carbon. So this will be 1.6 divided by 44.01. And then we can do the same sort of thing for water to get the mass or the moles of hydrogen. This is going to be 18.02. But how many moles of, what's the mole ratio of hydrogen to water? 2 to 1. So we'll get 2 moles of hydrogen for every 1 mole of H2O. So 0.819 divided by 18.02 times 2. 0.090899. I'm sorry, this is moles of carbon, moles of hydrogen. So what's my smaller number of moles? Carbon. So if I divide both of these by 0.036, this one is going to be 1. That's 36355. This one is 2.5. Again, can't have a fraction here. So can't have half a hydrogen. So we got to multiply these both by 2. So this is C2 H5. Unless I made a mistake. I don't know how you have a molecular formula of C2H5. Huh? It's what? Illegal. Yeah, it is. Huh? Sorry, no, it's just because it just taught OChem, this chemical formula doesn't work. Not a real thing. It's fine. It's fine for this. It's fine for this. We did everything right here. Sorry. I'm pretty sure it is. Mm-hmm. It's 12.01 plus 16 times 2. Yeah, okay. Sorry. Too much OChem makes that just, it hurts. So C2, H5. Ugh, makes my skin crawl. Okay, so we got another sample here. Let me just, you know what, the chemical reactions are going to be pretty quick because we're not really doing more than just balancing them. And I do really want to show you what happens. So we've got here a sample that has carbon, hydrogen, and oxygen. And in this problem, they also gave us, move this, right, the mass of the sample. We didn't get this in the last problem. We actually didn't need it in the last problem because all of our mass was from carbon and hydrogen. So we just assume that's where all the mass is. But now when we calculate, right, we're going to have to calculate how much carbon and how much hydrogen, but we added extra oxygen to this sample. So we're going to need to know not just the moles of carbon and not just the moles of hydrogen, but also the mass. And that will give us some mass that should be less than this 0.8008 grams because there's carbon, hydrogen, and where does the rest of the mass come from? The oxygen. So we can start this exactly the same way. And 44.01. And so this is going to look very similar because we'll get 1 mole of carbon for every 1 mole of CO2. And then we come through and we do hydrogen. So 0.655, and that's 18.02. This is exactly the kind of thing that if you like did this routinely, you'd just have a spreadsheet, right? Because it's always carbon dioxide and it's always water, so you'd be doing the same exact calculations over and over again, which is good because it's pretty simple. But when you're writing everything out by hand. Okay, so if I calculate the moles, 1.6004 divided by 44.01. Don't need to worry about the ratio. That's 0.0363634. And that's moles of carbon. And then 0.6551 divided by 18.02 times 2 is 0.72708.102. Okay. So in terms of doing our empirical formula, we need those in moles. So we can just leave those there, but we need to account for that oxygen first before we go on to the next step, right? Because we don't know if the oxygen is going to be less moles or more moles than either of these. So I'm going to take my carbon. I'll take the moles of carbon over here in 0.036364 and multiply that by the molar mass. And the same for hydrogen. Multiplied by 1.01. And then I'll add those together. So 0.51017 grams. So that mass is the mass that we can account for from hydrogen and carbon. Like I said, 0.51, that's less than 0.8. Yeah, question?
It should have been 0.07 mole.
Yep, you're right. And I actually used the correct number because I just copied it from my calculator. So 0.51 is correct. All right, so this, I just calculated the mass of carbon from the moles and the mass of hydrogen from the moles. And now I didn't write this in a way very conducive to the space. Ooh. So if I take 0.8009 grams minus that, that's 0.29073 grams of oxygen. And now we can divide by that. Now we just need the moles of oxygen. So divide that by 16. Great. So now that is our smallest number of moles. Divide these. That equals 2. Oh, I didn't fix this one. 727.08102 divided by, that's 4. And this is divided by itself, so it's 1. So that'll be C2H4O. That chemical formula probably works. I won't bother. Chem stuff. Okay. Cool. Any questions? It's a lot of math. Not hard math, it's just a lot of steps. Just try and remember why you're doing each step. Ultimately, we need to get to moles of the things that came from our compound. And when oxygen's involved, you have to find the mass of oxygen as the difference, right? Because we can account for most of the mass, but not all of it. I will say that this kind of problem probably not going to show up on exams because it's really time consuming and it tests you on one concept. Not very efficient, especially since I think the first exam is in lecture, so limited on time there also. All right, chemical reactions. I think you guys already know what chemical reactions are, but we'll go over it real fast. All right, chemical reactions involve chemical changes. Talked about chemical and physical changes. These involve a rearrangement and exchange of atoms to produce new molecules, but we're always using the same atoms. I was gonna give it, actually I bought a Lego. I always think of atoms like Lego, right? And you could take them apart and you could build new things, but you keep all the same pieces, basic pieces. The kit that I bought is actually one of those ones where it's got a bunch of different things that you can make out of all of the different pieces. And so chemical reactions are like taking apart your Lego rabbit or whatever and then turning it into a whale. So you might not need all of those pieces to make the whale, but you need some of them and you might need to add something else to get other pieces. And you always usually end up with something left over also, which is where we'll start to diverge from Chem 20 stuff, but you get the idea. We're taking these atoms and we're rearranging them or creating new molecules. The combustion reaction talked about in the combustion analysis is one type of reaction. We're taking some compound and we're converting it into carbon dioxide and water by combining it with extra oxygen. We use those for just so many things. In any chemical reaction, you're going to have reactants, you're going to have products. So reactants are on the left side of the equation. That's what you're putting in. Those are the things that react. Products are the things that are produced. And so they come out on the right side, just like a sentence. You read it left from right, it describes a process. They also provide information about the reaction. So we can have things like formulas, states of the reactants. Most of them are self-explanatory. G is gas, L is liquid, S is solid. Aqueous is the only one that's weird, that you probably couldn't guess if you hadn't seen it before, but it just means that it's in a solution of water. So it's dissolved. And then normally when you're writing the L for liquid, it's a cursive L, if you're handwriting it. Also tells you about the relative numbers of the reactant and product molecules. So how many atoms of each type do I need to go into this, or how many molecules of each type do I need to go into this to get however many that come out? So then we can use that to determine the masses of reactants used and products made. So we take methane and we burn it. So we could do a combustion analysis of methane. That's what I was expecting that other problem to be, but methane burns to produce carbon dioxide and gaseous water. And so it's also natural gas. So your heater or stove at home might use this. If you look closely at the equation, we have carbon, we have one carbon, 4 hydrogens, 2 oxygen atoms, but on the right side we have 3. So we can't just pull an oxygen atom out of nowhere. It has to come from somewhere. And it has to come from another oxygen. So we have to balance these. Other problem here is that the number of hydrogens doesn't match up either. So we're currently violating the law of conservation of mass. Basically, 2 hydrogens need to be destroyed, and 1 extra oxygen needs to be created out of thin air. We're not magicians, unfortunately. So when we're balancing these, you might have previously just thought of it in terms of, I need the number of letters on this side to equal the number of letters on this side, and I can only do that by changing the numbers in front. And that works mostly, right? In terms of solving the problem, getting it right, that works. You need to keep in mind that we're talking about, like this CH4 is describing a carbon atom with 4 hydrogens attached. And each of these oxygens is describing 2 oxygen atoms that are attached to each other. And on the other side, we're rearranging them. So 2 of these oxygens have to go to the carbon, and 2 of them have to become water. And normally we do this with the simplest ratio. But whatever the ratio is, it has to work out so that we can account for all of these pieces going into all of these pieces, at least in this chemical formula. And really, when we're looking at these, we're going to talk about these numbers, these coefficients, too. And then there's, if you remember, an implied 1. Very often, we're going to just call this 2 moles of water. But really, the balanced chemical equation is talking about a molecule to molecule, right? 1 molecule of this, 2 molecules of this, makes 1 molecule of this and 2 molecules of that. And the reason we can scale that up to moles is because moles is just a number of those molecules. Right? I can say dozen, right? 1 dozen, that's a weird looking 1. Let me fix that 1. It looks too much like a 2. I'll just do that. I could say 1 dozen CH4s. I could say 2 dozen oxygens. It's just the count of them. So when we're talking about these reactions, we're almost always doing them, could almost say we're always doing them at larger scales. So we can just convert these to moles. All right, so how many oxygen atoms are on the right-hand side of this following chemical equation? Think so? Wait, 9? On the right-hand side? So because there's a 2, that means that there's Fe2, Fe2O3, and CO2, CO2. And so we multiply the coefficient by the subscript. So this would give us 8. This would give us 6. So we have a total of 14 oxygens. How many are on the left side? Also 14. Oxygen, more than anything, will end up in multiple parts of a reaction, so you got to be careful that you make sure you're counting all of them. More than most, those get forgotten or missed. All right, so you probably balanced chemical equations before, but these are some general guidelines. This is like doing a Sudoku or any other kind of puzzle. There's more than one way to do it. Oftentimes, there's an easier way to do it and a harder way to do it. These are just some guidelines to help you get you there. Probably the one thing that you always have to do, unless it's already given, is write a skeletal equation. So that's just formulas of reactants, formulas of products. In the pre-lab, you had to do that for one of them. Write out the skeletal. In today's lab, we'll have to do more of those. And then this next step is the one where it'll save you some time. Right, so balance the atoms that occur in more complex substances first. And always balance atoms and compounds before atoms in pure elements. Does anybody know why? So if I go back to this, so why do I want to balance? Right, it says always balance atoms in compounds before atoms in pure elements.
Just from a logical standpoint, if you have to go back and change the number of a compound with multiple elements at the end, it's going to change the number more than one element. So you're going to have to change more.
Exactly. If I change this, and then I have to go change something else, especially in this problem where iron, if we ignore the fact that there's already coefficients in here, right, if we have to change the number of irons, we change the number of carbons. We're just changing this number in front. That also changes the number of oxygens. Now over here, I've got a really easy way to add oxygen by itself without changing anything else. So it's like the last piece that you want to move because it doesn't move any other pieces. Always balance compounds first. Similarly, balance atoms that occur as free elements last. In the previous problem, oxygen's by itself. Again, it doesn't move any other pieces. And so we can always come back and use that to fill the gap for the rest of the oxygens. You guys might be afraid of fractions, but if the equation contains coefficient fractions, clear them by multiplying the entire equation by the denominator of the fraction. The fractions actually make it pretty easy to balance, especially combustion problems. And I'll show you how. And then the last step, of course, is to check, right? Make sure it's actually balanced. All right. So what's the formula for silicon dioxide? SiO2. And it's a solid, so a little parentheses S, solid carbon, to produce silicon carbide and carbon monoxide gas. So carbon monoxide, I think silicon carbide is just SiC. Yeah, okay. That one's a little bit weird. I would have expected it, especially in the textbook, to be silicon like monocarbide, because it's just one carbon. And usually, if it's two nonmetals, then the second one gets a prefix, regardless of if it's one or not. Okay, so where should I start balancing this? Yeah, so we can start, if we start with silicon. If we start with the very left one, right? Silicon, yeah, already balanced. Oxygen, though, is a good second one to do. Why would I want to balance oxygen before I balance carbon? Carbon's by itself, and it's in two places over here. So if I change this, then it's going to change carbon, and I have to come back and change it again. We'll leave carbon for last. So to balance the oxygens, I'll put a 2 there. And now how many carbons do I have? 3. So we got 2 here, 1 there. So nice, easy 3. Okay. Perfect. Okay, so now we got gaseous ethane, C2H6 gas. I already wrote it. So this is a situation where if it says gaseous oxygen, that means O2. Carbon dioxide, H2O. Cool, so similar kind of thing. What do I want to balance first? Carbon? Yeah. Or hydrogen. And really, in any combustion problem, balance carbon first, or balance hydrogen first. Balance carbon and hydrogen first, then check your oxygens. So I need 2 carbons, and I need 2 carbon dioxides, 3 waters. Because I've got 6 hydrogens in my reactants, and I need 6 in the products. So my products, how many oxygens do I have? Stupid bug. Sorry. Good on you guys for focusing. There's 7. All right. So can I just put a 7 there? No. Can I put 3 halves? No. Yes. So the easiest way to handle this is say, I can't put 3.5 because I can't have half of an oxygen. So just put 7 over 2. Because I've got 2 of these, if I multiply that by 7 over 2, I'll get 7 oxygens. Now the problem is that I can't really do that. I can't have an improper fraction of this, because that would be 3.5, and I can't have half of that. And this is where you just multiply everything by 2. So I'm going to do this. We'll multiply everything by 2. But I can duplicate. When you're doing this, probably just erase these. Right, so this will be 2, this will be 7, this is 4, and this is 6. If you need, and like if this was 03 and I needed 7, then I'd do 7 over 3. Right? It's whatever this number is here, that's what determines the fraction that you use.
Will it ever be like oxygen by itself, or will it always be like O2 or O3 or something like?
Usually it'll be O2. I can't say that it won't ever be just oxygen. It could. Probably always going to be O2 though. Yeah. Okay, and then just the last one here. Timing worked out really nicely, actually. Write a balanced chemical equation for this one, and we've got particularly here polyatomic ions, which is part of why I printed those polyatomic ion sheets out for everybody. You should work on memorizing those. So if we have lead nitrate here, I did a weird thing. I'm gonna have 2 of those. And aqueous potassium chloride. I'm glossing over the over like the naming stuff because we're going to cover that next week. PbCl2. That's a solid. Potassium nitrate. Okay. All right, so the whole point of this slide is that these polyatomic ions, this is another reason that you should memorize these, unless we're talking about redox reactions, which we'll get to later, they pretty much always stay as a unit. So the nitrate will move around as nitrate. So don't try to balance the nitrogens and the oxygens of nitrates separately, just balance the number of nitrates. And it's a lot easier to do that and remember to do that if you've memorized the polyatomic ions. So you recognize, oh, NO3, that's nitrate. Or in a problem like this, it says nitrate. So if we're starting this one off to balance, how many nitrates do I have? So how many nitrates do I need over here? 2. So I just add a coefficient of 2. Now this is also a, does anybody know what type of reaction this is in terms of what the atoms are doing? Is a precipitation reaction. Nice. Double displacement is what I was looking for. Yeah, it's a double displacement reaction. So if I change this coefficient, I changed the nitrates, now those match, but I also changed what? Potassium. So usually, and especially in double displacement reactions, I start with 1 and then I say, okay, I changed nitrate to balance, now I need to do potassium. How many potassiums do I have over on the reactants? Just 1, so I need a 2. And now because I added that 2, I changed the number of chlorides. So I say, okay, now I've got 2 chlorides. How many chlorides? Oh, it's already 2. And then just for completeness, we could say, okay, lead, 1, 1, so it's done. Double displacement reactions tend to be some of the easier ones to balance for that reason. And especially if you're just balance nitrate as nitrate. Don't balance it as nitrogens and oxygens. Cool. Are there any questions?